everybody. This is a video series covering a college semester of circuit analysis. Although YouTube already has channels that teach circuit analysis, this video presents a step-by-step example-based approach so that anyone with some background in calculus will be able to understand circuits. So, what is a circuit? I would say that a circuit is any time you have some power source connected in a closed loop to some load or element. On the screen, I have drawn a battery and a light bulb. Right now, you do not have a circuit because there isn't a closed loop between the battery and the light bulb, but we can make a circuit by using some wires. So now I've added some wires. These orange wires can just be some copper wires. Notice that for the battery, I've included the positive sign, meaning the cathode of the battery, and the negative sign, meaning the anode of the battery. Now you have a circuit because now you have a closed loop. Because you have established a circuit, the light bulb will light up. So why does a light bulb light up? The answer is that you have electrons, which are negative charges, leaving the anode of the battery. So here I've drawn the electrons leaving the anode of the battery and moving in a counterclockwise direction. So the electrons leave the anode, move up the light bulb, which causes it to turn on, and then across the top wire and into the cathode. But negative charges moving in a counterclockwise direction is equivalent to hypothetical positive charges moving in a clockwise direction. This flow of positive charges is known as electric current. So, why do we choose to have positive charges? The reason is that we prefer to use positive values instead of negative values. So, in order to use positive values, we pretend that the electric current is defined as positive charges moving in the opposite direction of electrons. Current is measured in units of amperes and is represented by the symbol I. If the current is a constant value, like 4 amperes, then you can use a capital I. But if it is variable, then you use a lowercase I. In this example, you have a light bulb as our load or our element, which is just a thing that receives power from the source. But you don't have to draw it as a light bulb. We can use some generic symbol to represent our load. I have replaced the light bulb with a zigzag symbol that represents a resistor or a resistive load. I will explain what a resistive load is later. There are other types of load, but a light bulb is mostly a resistive load, and a resistor is probably the most common type of load that you will have when you start with circuit analysis. So now that I've explained current in a very general sense, what is the dictionary definition of electric current? Well, an electric current is defined as a flow of charge per unit time. And to explain this definition, I will give an example. So let's say that you are looking at the wire at some particular point. Let's say that you are looking at the purple point. For example 1, you see 8 coulombs of charge pass by in 2 seconds. What is the electric current? The answer is just 8 coulombs divided by 2 seconds, which equals to 4 amperes. Now, this is an average current because 2 seconds is actually a very long duration of time. For a very small instant in time, we need to define an instantaneous current. So, in this equation, you see that a very small amount of charge dq passes by in a very small amount of time dt, and this is defined as the instantaneous current. You can also rewrite the equation as dq equals I dt. Now, this is useful because if you integrate both sides, then you can find the total amount of charge q that passes through any point over any specified period t. So here, I have expressed the total charge q as a time integral. Now, the way I've written the integral, some people have a problem with this. The reason is that I have used the t symbol here for dt, but my upper limit of integration is also the t symbol. And usually, math people don't like this. So instead of using dt, they will replace dt with d tau or some other dummy variable. But personally, I don't think it matters. Now, for example 2, you have a circuit with a current of 3 amperes for 2 seconds. How much charge passes through the resistor? Starting with our integral formula, we notice that because the current is a constant value, the value I can be taken out of the integral. Next, we perform the integration. Now, you see why some math people is annoyed because my upper limit of integration is t, and I'm using that to substitute into my variable, which is also t, but I don't think that this is an issue. So now we apply the upper and lower bounds of the integration, and finally we get the result that Q is equal to I times T. And from a unit analysis perspective, Q equal IT makes perfect sense. So our answer is 6 coulomb. For example 3, we are given a current that is not a constant, and we want to find the charge Qt for any time t. So we start by writing out the time integral. We enter the expression for the current. We perform the integration using the power rule. We then apply the upper and lower bounds of the integration, and then we get our result. Now in example 4, we have the opposite problem. We're given the expression for the charge Qt, and we are asked to find the current IT for any time t. So we start with our formula for current. We enter the expression for the charge. We perform the derivative, keeping in mind the chain rule, and then we get the result. To explain voltage, I will use the analogy of a pump and water wheel. Here, a motor and pump and 2 pipes are used to pour water onto a water wheel. The bottom pipe is lying on the ground, so its height is 0 feet. The top pipe is 1.5 feet above the ground, so its height is 1.5 feet. The blue dots represent water. Here, the height y represents a gravitational potential. At locations 1, 2, and 3, the value of y is the same. It is 1.5 feet. At location 4, the water drops 1.5 feet. In other words, we can say that there is a 1.5 feet drop in gravitational potential across the water wheel. At locations 5, 6, and 7, the value of y is the same. It is 0 feet. Now, look at the water at location 7. This water will get pumped up to location 1. In other words, the motor and pump will increase the gravitational potential of the water by 1.5 feet. So we can ask, how much energy does the motor need to exert to do this? Physics tells us that the spatial derivative of a potential energy function is equal to the negative of the force of the interaction. The equation can be written like this. Here, U stands for potential energy, F stands for force, and Y is the direction of the movement. When a mass moves upwards, the force against it is gravity. So we can replace F with negative mg, where the negative sign is due to the force of gravity pointing downwards. We can then rearrange the equation as follows. This equation tells us that it takes an energy du to move a weight mg up a gravitational potential dy. With voltage, we have a very similar situation. Here, a battery and 2 wires are used to turn on a light bulb. The bottom wire is considered ground, so its voltage is 0 volts. The top wire is 1.5 volts above the ground, so its voltage is 1.5 volts. The blue dots represent positive charges. Here, the voltage V represents an electric potential. At locations 1, 2, and 3, the value of V is the same. It is 1.5 volts. At location 4, the charges experience a voltage drop of 1.5 volts. In other words, we can say that there is a 1.5 volt drop in electric potential across the light bulb, which we can denote by drawing a plus sign, a minus sign, and the number 1.5 next to the light bulb. At locations 5, 6, and 7, the value of V is the same. It is 0 volts. Now, look at the charges at location 7. These charges will get pumped up to location 1. In other words, the battery will increase the electric potential of the charges by 1.5 volts. So we can ask, how much energy does the battery need to exert to do this? By making an analogy to the water pump, we can write this equation. This equation tells us that it takes an energy dW to move a small charge dQ up a voltage gradient of V. Here we put the two cases of gravitational and electric potential side by side. As you can see, they are the same concept. So now we have our formal definition of voltage. Voltage is an electric potential. It is defined as the work needed to move a positive unit of charge from the negative terminal of a voltage source to the positive terminal of a voltage source. For example 5, how much energy does it take to move 10 coulombs of charge from the negative terminal to the positive terminal of a 1.5 volt battery? We start with a formula for voltage. We can then rearrange the formula like this. And then we can input the value for voltage and for the charge, and we get 15 joules. Here are some final tidbits. We have a circuit with a 1.5 volt battery. The entire length of the wire connected to the positive terminal will have 1.5 volts. The voltage doesn't change until there is some voltage drop or voltage rise. The same applies to the entire length of the wire connected to the negative terminal. So, the concept is that the voltage everywhere along a wire should be the same. For the wire at 0 volts, you can also put a ground symbol. This isn't absolutely necessary, but it's good practice. Here, we can look at what happens when you have multiple batteries. What is the voltage at point C? Well, voltage is a difference of 2 points. So when someone says voltage at point C, they mean voltage at point C relative to the ground. So in this example, it would be 3 plus 5 plus 6, or 14 volts. Whereas the voltage at point B is B to ground. So it is 11 volts. And for point A, it is 6 volts. Now where's the voltage between point C and B? So since C goes first, it will be positive 3 volts because point C is 3 volts more than point B. Now the voltage between point C and A would be 8 volts. Because you can see there's a 3 volt battery and a 5 volt battery between points C and A. But if you ask where is the voltage between points A and C, well, A is lower than C, so it would be negative 8 volts.